Assalamualaikum and a very good day to everyone. Today our team will be presenting on IBG216 Introduction to Bioreactor Operation, Design and Calculation. Before we begin, we have prepared this QR code on the screen, which you can scan to find information about our Group 1 team members. Without further ado, let's dive into our presentation. To give you a quick overview, bioreactors are specialized systems engineered to maintain the perfect controlled environment for microbial growth and product synthesis. In this specific study, we are looking at how changing glucose concentration in the YPEG medium affects three key areas: biomass yield, substrate consumption, and ethanol production. To make sure our process stays stable and contamination-free, we combine strict aseptic operation with precise and analytical testing. Specifically, we use UV spectrophotometry to track biomass, the DNS method to measure reducing sugar, and GCFID to quantify our ethanol concentration. Moving on to our core objective, our study focused on three main goals. First, we want to analyze the specific effect of varying glucose concentration within the YPEG medium. We are closely monitoring how these changes impact microbial growth, glucose consumption, and ethanol production. Second, this project allows us to gain hands-on understanding of the hardware structure of bioreactors alongside mastering aseptic sampling technique and complex sterilization procedure, both of which are critical to preventing contamination. Finally, we aim to evaluate and compare the performance difference between our reactor system using precise analytical method. To do this, we are determining biomass concentration using a UV-Vis spectrophotometer at 540 nanometer, measuring reducing sugar concentration via the DNS method, and quantifying ethanol output using GCFID.
Conduct the fermentation using bioreactor, we shall disembowel the bioreactor first. To disassemble the bioreactor, we must first remove the motor driver and the exhaust. After that, open the clamping to take out the bioreactor to put in the media. Preparing the media. We need to prepare 10 gram of YPEG, 5 gram of glucose, and 20 gram of peptone. After that, we mix all the substance together in a beaker with 1 liter of distilled water and make sure they are dissolved completely in the distilled water. Then the media is ready to be poured inside the bioreactor. After the media is transferred, we need to cover all the tubes of the bioreactor with aluminum foil before autoclaving it to prevent contamination. Then, we will start autoclaving for about 1.5 hours. After the autoclave done, we shall leave it to cooling down first before we insert it back into the bioreactor. Then, we will need to reassemble the bioreactor and start to inject the inoculum before we start the experiment. During the injection, we need to make sure that we are doing aseptic techniques to prevent contamination. After the injection of inoculum, the time starts to count. And then we need to take the sample based on the interval time to conduct 3 analyses. The first one is the absorbance reading by using UV spectrophotometer, while the second one is the absorbance reading by DNS method. The last one is the gas chromatography method. These 3 methods help us to determine the yeast growth during this 24 hours interval.
Assalamualaikum and hi. Today we will present and talk about this bioreactor operation. So this is the motor driver. The function is actually to stir the microbes or any components in the bioreactor. And this is the exhaust, and it has a vapor inside it. And the component that we will take out is actually it has a fan inside it. And this is the clamping. The function is just to lock the bioreactor, and we will open it by taking out the head plate for autoclave process. So after the autoclave process, we will put back these components. There will be a pipe here which can cover your sample everything. And we will clamp the head plate just to ensure it is stable enough during the reaction. This is the control of the bioreactor. So how you set everything is you can just, let's just say we do temperature. And next we will put back the fan here. So this is what will happen. So also we'll lock in to make it stable. And then pH you can set, your oxygen you can set. And then if you realize there will be acid or alkali or base to maintain the pH of the sample. So this is the components inside the bioreactor. This is the blade, and this is the impeller, and this is the shaft. So the main function of this component is actually to mix the things, or for example microbes, in the bioreactor during the process. And this is the baffle. It's like a very thin layer component, and the function is actually to prevent the vortex formation. This is the spudger. So the function of the spudger is actually to supply air, oxygen or gas during the process. And this is the components to control the temperature during the process. And this is the O-ring of the bioreactor. And these two components of the bioreactor known as the jacketing. And the function of the jacketing is actually to ensure uniform distribution of temperature during the process. It is important so that bacteria or microbes placed in this bioreactor can grow at optimum level. So we will place a tube for the jacketing from below to top to prevent the leakage of the water. And this component is really important to make sure the temperature is uniformly distributed.
Assalamualaikum, Doctor. I am Adrina and I will explain about the results obtained by Group 1 in this experiment. So this is regarding the microbial growth rate. Table 1 shows the optical density, which is the absorbance obtained at 540 nanometer, and the biomass of Saccharomyces cerevisiae. So to calculate the biomass, I can actually use a standard calibration curve obtained from the previous experiment. So the linear equation is y equals to 1.65x minus 0.53 is used for calculation of biomass, where y represents the absorbance at 540 nanometer and x represents the biomass in milligram per mil. So I rearrange this equation and I've got biomass is equals to absorbance plus 0.53, which is the y-intercept divided with the slope, which is the gradient. The value is 1.65. So figure 1 shows the relation of graph of absorbance at 540 nanometer, which is the OD, against the time in hour. So by using the equation, I can actually plot the graph of biomass in milligram per mil of yeast growth against time in hour. So by plotting the graph, I can actually observe the 4 phases of biomass produced. So the first phase, known as the lag phase, which is at interval time at 0 to 3 hours, and at this phase, the yeast is actually adapting to the new environment. That's why the biomass change or produced in this phase is quite in a smaller number or smaller value. And the next phase, known as the log phase, which is at 5 to 15 hours. This is also known as the exponential phase. So at this phase, the yeast cells, which is Saccharomyces cerevisiae, divide at the maximum rate. And we can actually obtain the specific growth rate by changing this phase into the ln biomass graph later. The third phase, known as the stationary phase, which is at plateau at 15 hours to 23 hours. At this stage, the rate of the cell growth is actually equals to the rate of the cell death. And lastly, the yeast will undergo some kind of depletion phase, which is at after 23 hours. Because at this condition, the yeast is experiencing nutrient exhaustion and toxic buildup. So to calculate the specific growth rate, I can actually change the biomass into the natural logarithm of biomass, which is ln biomass, shows in table 2, in log phase growth of Saccharomyces cerevisiae at specific time, which is in hour. So by obtaining the data from this table, I can actually plot the figure 3, graph of natural logarithm of biomass, ln biomass, against time in hour. So by plotting this graph, we can actually obtain the positive linear equation here. So the equation is automatically generated from the Microsoft Excel application. Y is equals to 0.0363 x minus 0.3591 with a very high r square value, which is r square equals to 0.9326, and this shows that the results obtained is reliable. So specific growth rate mu per hour can actually be obtained directly from the gradient of this straight line graph. So mu is equals to gradient of the graph, whereas mu is equals to 0.0363 per hour. Means that the specific growth rate of the yeast is actually 0.0363 in 1 hour. So next, we can actually also calculate the doubling time, which is TD in hour. So TD can be calculated by using the formula TD is equals to ln 2 divided by mu. So TD is equals to ln 2 divided by 0.0363, and I can get TD is equals to 19.095 hour. So this is regarding the DNS analysis to show how much the DNS consumed by the yeast in the bioreactor. So table 3 shows the optical density at 540 nanometer and concentration of glucose consumed by the Saccharomyces cerevisiae. So the same method to calculate the concentration of the glucose, which is using the standard calibration curve obtained from the previous experiment, y equals to 1.1799x plus 0.1952, where y shows the absorbance and x is the concentration of the glucose. So to calculate the glucose, the same method, I rearrange the curve. Glucose concentration, milligram per mil, is equals to absorbance minus with the y-intercept, C value 0.1952, divided by 1.1799, which is the slope. And these are the two graphs obtained from the data. So figure 4 shows the absorbance at 540 nanometer against time in hour, and figure 5 shows a graph of glucose concentration in milligram per milliliter against time in hour. So the glucose, from the graph, we can actually see the glucose shows a negative linear relationship with time. Means that as the time increasing, the yeast will consume more glucose. So that's why the glucose is decreasing. So from figure 5, I can get the linear equation y is equals to negative 0.0337x plus 1.225 with r square value equals to 0.9776. And for figure 4, the linear equation obtained is y is equals to negative 0.0397x plus 1.6407 with r square value 0.9775. So both graph shows a very high values of r square. And next is regarding the ethanol yield. The table 4 shows ethanol yield of substrate determination using the gas chromatography flame ionization detection by Saccharomyces cerevisiae. Again, the same concept or method I'll use to calculate the ethanol concentration. So ethanol concentration is calculated by referring to the standard curve obtained from the previous experiment, which is y is equals to 7 times 10 to the power negative 6x, where y is the peak area and x is the ethanol concentration. I rearrange the graph and I got the equation: ethanol concentration percentage volume per volume is equals to peak area divided by the slope, which is 7 times 10 to the power of negative 6. And finally, we can calculate the ethanol yield by using the formula of ethanol yield is equals to ethanol concentration, which is in volume percentage per volume, divided by the glucose consumption, milligram per mil, times with the 7.9 milligram per mil divided by the percentage of volume per volume. Why we choose the 7.9 here is because the density of ethanol at standard 30 degrees Celsius is 7.9 milligram per mil in volume, a percentage per volume. So this is the graph obtained for ethanol yield. The figure 6 shows the graph of peak area in MV or V against the ethanol concentration. And lastly, about a figure 7 shows a graph of ethanol concentration percentage volume per volume against a time in hour. And lastly, we can actually obtain the metabolic profile, which is shown on figure 8, graph of metabolic profile of Saccharomyces cerevisiae in the bioreactor. So this graph is important to show the trend of the biomass, glucose consumption, and ethanol, which are the 3 important parameters to analyze the yeast growth in the bioreactor. So, however, the ethanol concentration previously calculated in the units of percentage volume per volume now need to be changed into the milligram per mil. which is shown in table 5, ethanol concentration in unit of mg per mil at specific time interval in hour. That's all from me. Thank you, Doctor.
Thank you, Arjana. My name is Elchon Chakwani. Good day for everyone. Today I will present a discussion for experiment 2, which involved the operations of a 2-liter steel tank bioreactor using Saccharomyces cerevisiae cultivated in YPEG medium. The discussions mainly focus on the fermentation performance throughout the cultivation process, including microbial growth kinetics, glucose consumptions, ethanol productions, metabolic profile analysis, as well as the operational efficiency of the bioreactor system. Various analytical methods such as optical density analysis, DNS assay, and GCFRT analysis were used to evaluate the fermentation process comprehensively. While these experiments successfully demonstrate the capability of Saccharomyces cerevisiae to carry out glucose fermentation efficiently under controlled bioreactor conditions, the fermentation performance was monitored by analyzing biomass formations, substrate utilizations, and bioethanol production over time. The results often show a clear metabolic relationship between glucose consumptions, microbial growth, and ethanol accumulations. Overall, the microbial growth, the experiment, and also highlight the importance of the maintaining stable environmental conditions such as aerations, agitation, pH, and temperature to ensure efficient microbial activity and stable fermentation performance. Additionally, based on the Table 1 and Figure 1, the optical density at the 540 nanometers increased progressively with increasing fermentation time. These trends indicate a continuous increase in the concentrations of Saccharomyces cerevisiae cells inside the bioreactor. While for the optical density measurement is commonly used as an indirect method for estimating microbial growth because microbial cells scatter light passing through the culture medium. As the yeast population increased, the more light scattering occurred, resulting in high adsorbent values. Initially, the increase in the OD was relatively slower because the yeast cell were still undergoing adaptation during the lag phase. During this stage, the cell synthesis intracellular enzyme and metabolic intermediates necessary for growth. After adaptations, the cell enter the exponential phase, and where rapid cell divisions and active glucose metabolism occur, leading to a stepper increase in the OD values. While for our Figure 2 shows that biomass concentrations increase continuously throughout the fermentation process, the biomass strength closely corresponded with the optical density trends, indicating that OD measurement was reliable for estimating microbial growth. The increase in biomass concentrations occurred because glucose was actively converted into cellular components such as proteins, lipids, nucleic acid, and structural carbohydrate required for cell growth and proliferations. In addition, the efficient operations of the bioreactor contribute significantly to biomass formations. The 6-bladed disc impeller enhanced mixing efficiency and oxygen transfer, while the buffers prevented vortex formations and improved mass transfer throughout the fermentation broths. This mass transfer throughout and which is the conditions ensure the homogeneous nutrient distributions and supported continuous microbial growth during the fermentation. And now let's look at the table 2 presented the natural logarithm of the biomass concentrations or in the biomass. During the logarithm growth phase of the Saccharomyces cerevisiae, the purpose of converting biomass value into logarithm form was to evaluate microbial growth kinetics more accurately and determine whether the cell follow exponential growth behavior. The increase in biomass values indicate that the yeast cell underwent exponential growth throughout the log phase. This demonstrates that the microorganisms were actively dividing at a relatively constant rate under favorable fermentation conditions. The result also suggested that nutrients were sufficiently available and that environmental conditions such as aerations, pH, agitation, and temperature remained suitable for microbial proliferations. And here is also the equations which is used to interpretations of the table 2. Well, let's look at the Figure 3, which shows a linear relationship between long biomass and fermentation times. These linear trends confirm that Saccharomyces cerevisiae follow exponential growth kinetics during the logarithms phase. The slope of the graph represented the specific growth rate of the microorganism, where a steeper slope indicated faster microbial growth and higher metabolic activity. The linearity observed in the graph suggests that the environmental conditions inside the bioreactor remain relatively stable throughout the cultivation period. Adequate nutrient availability, proper oxygen transfer, efficient mixing, and controlled temperature and pH contributed to maintaining continuous microbial growth. If fermentation had continued for a longer durations, the culture would eventually enter stationary phase due to nutrient depletion and also the ethanol accumulation. And let's look about the figure 4, which shows that the absorbers at 540 nanometers decrease gradually with increasing fermentation time. The decrease in OD value suggested a reduction in suspended yeast cell concentration in the fermentation broth. This phenomenon may have occurred due to nutrient depressions and also the reduced microbial activity, cell sedimentations, and increasing ethanol accumulations throughout the fermentation process. As glucose concentration decreased and ethanol concentration increased, the yeast cell experienced greater metabolic stress, which gradually reduced cell viability and proliferation rate. Ethanol accumulations can negatively affect yeast cell by disrupting membrane integrity, altering membrane permeability, and reducing enzyme activity. Consequently, the culture gradually transitions from the exponential phase toward the stationary phase, resulting in lower OD readings. And while for our linear relationship, we observe our R squared is equal to 0.9775, which is show a very good linear relationship in this graph. And let's continue. Based on the table 3 and figure 5, glucose concentrations decrease progressively throughout the fermentation process. This trend indicates that glucose was continuously utilized by Saccharomyces cerevisiae as the primary carbon and energy source for biomass formations and ethanol productions. The decreasing glucose concentrations reflected active microbial metabolism through glycolysis, where glucose molecules were converted into pyruvate while generating ATP and also the NADH. Under fermentative conditions, pyruvate was subsequently converted into ethanol and carbon dioxide. The inverse relationship observed between glucose concentrations and also biomass formations confirm efficient substrate utilizations by the yeast cell during the fermentations. And not only that, based on the table 4 and figure 6, ethanol concentrations increase continuously throughout the fermentation process. This indicates that Saccharomyces cerevisiae successfully converted glucose into ethanol through an aerobic fermentation pathway. Initially, ethanol concentration was relatively low because the cell prioritized adaptations and biomass synthesis. However, as fermentation progressed and glucose metabolism intensified, ethanol production increased significantly. Additionally, the GCFID calibration curve shows strong linearity between ethanol concentrations and also the peak area, confirming that the analytical method used for ethanol quantification was accurate and reliable. The increasing ethanol concentrations clearly demonstrate successful fermentation activity throughout the cultivation period. While as ethanol accumulated continuously in the fermentation's broth, inhibitory effect on microbial activity gradually became more significant. High ethanol concentration can disrupt cell membrane integrity, reduce membrane permeability control, denature intracellular enzymes, and interfere with nutrient transport mechanism. As a result, yeast cell viability and metabolic efficiency gradually decrease, causing slower biomass formations and reduced fermentation rate during prolonged cultivations. Ethanol toxicity is therefore one of the major limiting factors in industrial fermentation process because excessive ethanol accumulations can eventually inhibit further microbial growth and also the product formations. And now, let's look at the figure 7, which illustrates the overall metabolic profile of the Saccharomyces cerevisiae throughout the fermentation process. The graph shows that the biomass concentrations and ethanol concentration increase continuously, while glucose concentration decreased progressively over time. These metabolic relations confirm that glucose was actively converted into both cellular biomass and ethanol during fermentations. Initially, glucose was mainly utilized for rapid cell growth and biomass formations. As microbial population increased, metabolic activity intensified, causing higher ethanol accumulations at later fermentation stage. Overall, the graph followed the expected pattern of the microbial growth kinetics and product formation is in yeast fermentation system. Lastly, the successful fermentation performance was strongly influenced by the operational efficiency of the steel tank bioreactor system. The 6-bladed disc impeller enhanced agitations and oxygen transfer, while the spatula improved aeration efficiency by distributing sterile air throughout the fermentation broth. Additionally, the pH probe and dissolved oxygen probe allow continuous monitoring of critical fermentation parameters to maintain suitable growth conditions. Several precautions were also important to ensure reliable experimental results. Strict aseptic technique had to be maintained during inoculations and sampling procedure to prevent microbial contamination. Proper calibrations of analytical instruments such as spectrophotometers and probes was necessary to obtain accurate readings. Furthermore, the fermentation broth needed to be mixed thoroughly before assembling to ensure homogeneous distribution of cell and also the metabolites. So that, in conclusions, this experiment successfully demonstrated the relationship between microbial growth, glucose utilizations, and ethanol productions in the still-tank bioreactor system using Saccharomyces cerevisiae. The increasing trends in biomass concentrations and ethanol productions, together with the decreasing glucose concentrations, confirm efficient fermentation activity throughout the cultivation process. The experiment also highlighted the importance of proper bioreactor operations, efficient aerations, and also the agitations, control environmental conditions, and accurate analytical techniques in achieving stable and efficient fermentation performance. Overall, the results obtained were consistent with the expected microbial growth kinetic energy and also the bioethanol production behavior in yeast fermentation system. And thank you. That's all for my presentation for the discussion part. Thank you.
So, as we can see from the result taken from another group, as the hours goes by, the biomass OD are getting increased from 0.7994 to 1.0570. The calculation of the standard curve can be seen from this explanation. This is the figure of graph at absorbance from X to Y time versus absorbance at 540 nanometer. And this is the concentration of biomass against time. Next, we are moving on to the concentration of glucose. We can see that moving along the time, the concentration of glucose is decreasing. This is because due to for the microbial growth, concentration of glucose decrease because it needs glucose in order for it to proliferate. This is the graph of absorbance against time and also the graph of glucose concentration against time. We can see the pattern is going down. And this is the graph or the result taken from the group looking at all glucose concentration, ethanol concentration, and its yield. We can see that while the glucose concentration is going down, the ethanol concentration also going up. This is because glucose is being used as the food or the nutrient that is needed by the microbial growth, while ethanol is the product of the growth. And this is the calculation to calculate the peak area against ethanol standard solution. And this is the graph. And this is the absorbance reading or the OD, optical density of the growth rate.